So this is just a really short introduction to the practical that you're going to do this afternoon. It's run by me and Andrea Minchella, who is going to speak briefly after my small intro about the toolbox that you'll be using to do this practical. So two things. So I'm just going to quickly run through why ice velocity is important, where change in ice speed has been observed and over what timescales they've been observed. I'm going to highlight the advantages of Sentinel-1 by comparing it with ERS, and then I'm going to briefly overview 3 techniques for measuring ice speed before running into what our study area is that you'll be looking at in the next 2 hours, and then Andrea will give an introduction to the toolbox that you'll be using as well. The introduction to the toolbox, I think, is mainly to provide you with a bit of insight into the things that it can do that you won't be doing during this computer practical. So, yeah. It can do more than just map ice velocity. So ice velocity measurements, they're really important for a number of reasons. There's a lot of overlap with the talk that I gave just before lunch, but ice velocity has increased, generally speaking, in areas where we've observed rapid ice thinning. It's important because if you see areas of rapid ice thinning, but they're not correlated with a speed up in the ice motion, then this can inform you about the type of processes that are occurring. So we expect dynamical imbalance to occur in areas where we see both of those two things happening in the same location. In areas where we see surface elevation change but no corresponding increase in ice speed, then it could mean that there's other things going on in that area, like, for example, maybe there could be changes in firn compaction or ice lowering that's not caused by a decrease in the amount of ice in the area. Yeah, knowing ice speed and where changes in ice speed occur can help us predict the onset and magnitude of future sea level areas that are sensitive to future sea level rise. You've seen these two before, so I won't dwell on it too much. But again, as I mentioned in my previous presentation, areas where we see the most rapid thinning, we also see corresponding increases in ice velocity. So this time round, you've got a different flavour of altimetry result. This is Mal's surface elevation change from the Cryosphere period, but it shows broadly the same patterns that you see from the longer time series that I showed in my earlier presentation. And again, that's the time series of ice velocity speed up that you're now familiar with from Pine Island Glacier. But speed doesn't change just on long time scales. We also see short-term fluctuations in ice speed, and they're interesting too. This is a map of Greenland. It's not all about Antarctica. There's been ice velocity speed up in Greenland as well. It's mainly been focused on the this coast just here, so the west coast of Greenland, and we've sort of seen a gradual progression of ice speeds increasing in these ice streams as you go further north. Haven't really seen such long-term rapid speed up in some of the very northern glaciers, but maybe that will happen in the future. It's something to look out for. And I'm not going to go into any detail about the picture on the right, but I just wanted to highlight, and I hope that Twyla will be talking about it later, but one of the really interesting things that we can do with ice speeds is by looking at how they vary seasonally, we can start to understand what factors and what processes might be influencing the way that different ice streams respond to environmental factors that affect them. So it's not just long-term speed up, as we've seen on Pine Island Glacier, we also see short-term variations in ice speed. And I think this plot from Ian is one of my favourites at showing seasonal changes, just because the temporal resolution of his GPS measurements is so good. So this is ice speed on this y-axis here through time on the x-axis. You can see it's from 2009 to 2014. Each of the different coloured lines corresponds to a different in-situ GPS point, which is shown on this map here. So this is Jakobshavn Spray. It's flowing from this side of the image through into the ocean here. You can see all of the melange, the ice melange in front of it. And you can see that there are a number of points that are colour-coded to correspond with these points on this graph here. It's really interesting, and this is the sort of temporal resolution that might be very challenging to get from satellites. But the GPS points that are located closest towards the carving front of this particular ice stream show the most marked increase in seasonal ice speed throughout the time period that he had those sensors out there. And I think that's a really valuable record to see that. We see much less pronounced seasonal speed ups on the GPS points that he had located further inland. So you can investigate that further to help understand what might be causing that. But we don't just see ice velocity variations due to due to seasonal changes, they can occur on even shorter timescales than that. So this is an example from Thwaites Glacier, and there will be some data that you could download from the data portal if you were interested to do so. Thwaites is shown in the map here. The large red area is the area of fast flow, and this ice stream is flowing from this side of the picture to that side of the image just there. What we've also done is we've extracted a transect of data across the middle of the fastest flowing region, which is what's showing in the animation below. The grey line marks the mean ice velocity up the centre of the transect, and the coloured lines indicate the ice speed measured on each individual image. But what you can see, and it's pretty, you can see it happening in the animation, but I think it's more clear on this less pretty graphic on the left-hand side, that in the portion of the ice stream that is grounded, so this section here that's not grey, you see a much more stable ice speed, but in the area where it is floating, you see that there's quite a large spread in comparison to the grounded section in the ice speeds that we're observing. So this can also indicate that maybe ice speed can be influenced by ocean tides again. So it's another shorter term factor that might influence ice speed in some areas. So today you're going to be using Sentinel-1 data, and the main reason for that is because it's the best current data set that's available for measuring ice velocity in terms of the SAR data sets. It's free to download. There's a really easy to use ESA data portal, which has everything online. You just can register and immediately you're granted permission to get access to the data, so it couldn't be easier. Historically, with the ERS archive data that you can also get for free, you do have to submit a proposal to get it, and so it's a bit more time-consuming, but not nearly so time-consuming as receiving boxes of CDs in the post and then having to read them into your computer. At least it's delivered over the internet these days. But in terms of the image and the satellite parameters, the ERS data was in a nominal 35-day orbit, whereas Sentinel-1 is in a 12-day orbit. That makes it much more easy for us to measure ice speed because features are more preserved over shorter time periods, so you're able to make a better quality measurement with a shorter repeat baseline. There are other factors, so there's a larger area covered. You can see, and this is again an image that's familiar from my previous talk, that this is the type of coverage we got from ERS-1 back in the early 1990s, but that's the coverage that we got in interferometric wide swath mode from Sentinel-1 last month, so much improved. And it's not just about the fact that there's a greater downlink capability for Sentinel-1. The size of the swaths is just larger anyway, so you cover a larger area with each image. So it's 100 kilometres for an old ERS image, but that's over doubled to 250 kilometres for interferometric wide swath mode from Sentinel-1, which is great. And where the ERS 1 and 2 satellites were more for just research and development purposes, there wasn't a dedicated acquisition strategy that meant we'd have guaranteed coverage over the ice sheets. Now we've worked with the space agencies and they've been really keen to help us try and acquire data on every single orbit. So every single time Sentinel-1 is passing over Greenland and Antarctica, and in fact many of the glaciers and ice caps as well in other areas of the world, data will definitely be acquired, so you can guarantee that you'll have an image every 12 days. So that's just a fantastic improvement on what we had before. And this is an example of some of the results that are now coming out of Sentinel-1. I think the image I showed you before of Eric's ice velocity map of Antarctica was completely game-changing, and I think to think that all of that volume of data could be processed, at the time it was phenomenal, because it just, to do feature tracking, it can take a very long time to physically process on the computer, and to have access to that large volume of data and to be able to process it within a reasonable time frame completely changed the way that we're able to observe the ice sheets in terms of ice speed. However, now that we've got routine data being acquired all of the time with Sentinel, we're able to produce full ice sheet velocity maps routinely every year or every 6 months, depending on how often a campaign is tasked. And this is an example that was produced by MVO as part of the Greenland Ice Sheet CCI, and it's a full velocity mosaic of Greenland, and they'll be producing again the same for the Antarctic Ice Sheet CCI. So whereas it took us 20 years to get to having one ice velocity map of Antarctica or Greenland, now it's the sort of thing that we're able to generate yearly, which is great, I think. So Just want to run through very briefly the techniques that can be used to measure ice speed. You've seen interferograms, and I went through the process of how they're computed all this morning, so I'm not going to go into that in any more detail. But the main thing to note is that it uses the phase information to measure ice speed. So it's a coherent technique. There is also a type of feature tracking that can be done that also uses the phase information, and that's called coherent feature tracking. We won't be using that today, but what we will be using is intensity feature tracking. So you saw some images in Andy Hooper's presentation of what the amplitude image of a SAR frame looks like. It's just a black and white image, and you can see features visibly in the SAR images. And you can track those features, such as crevasses or whatever they may be on the ice surface, and do a least squares fit between a prominent feature to measure the offset between two time periods. And that gives you a distance of motion within whatever the temporal baseline has been of the two images that you're tracking between. The advantage of intensity feature tracking over the coherent techniques, which are dependent on having phase, is that it means you can track motion between a longer temporal baseline pair, so maybe you can still get a bit of a result out of 35 and 40-day image pairs. But again, at a certain point, this stops being useful, and you do need to have too much change has occurred within the intervening time period. The advantage of intensity feature tracking as well is that you get a two-dimensional ice velocity image, and that's shown in these images just here. So I thought I'd show you a different area than what we've seen before. So this is a Russell Glacier catchment just on the West Greenland ice sheet. It's land terminating rather than the marine terminating ice sheet areas we've looked at a lot in the pictures I've shown you already. This is the range and this is the amplitude. I think I've got it the right way around, but you can just see that all of these little ice streams are all flowing in slightly different directions, and you can see that different motion is picked up when you observe it from measure the displacement in the different directions. You can mosaic different frames from different tracks. You can mosaic the total magnitude to produce an ice velocity mosaic over a larger area, and that's great. That gives you a good picture of the motion over a larger area. But I just want to point out that if you haven't previously converted the data when it's in this form, when it's in range and azimuth, your motion, if you've got a square pixel, you've got range motion which is in one direction and azimuth motion which is perpendicular to that. So you've got it in two directions, and when you initially get that from the offset tracking procedure, it's located in the same orientation as the pixel. Whereas what you actually want when you're mosaicing data from different tracks, because those pixels are going to be orientated. So if you imagine if you've got a pixel in the corner there, that will be, the right angle will be orientated slightly different than the pixel in the corner of this image here. So you need to convert that into a coordinate reference frame, such as polar stereographic coordinates reference frame, before you mosaic the separate parts of the separate velocity components. And if you don't do that, you can see that in an image like this, you're sort of getting a bit of ice flow in one direction, but you're not measuring the same thing because it's looking at it in a different angle from another track. So you have to convert into the coordinate reference frame before you mosaic the separate X and Y components of the velocity image. So you don't have to do that today, but that's just something to bear in mind for people that do want to do more of it. You don't have to just be tracking velocity on grounded ice. You can get motion of other things that are within the frame as long as they're not moving too fast. So in this image frame, it's Thwaites Glacier again, you can see that you are tracking the speed of things like sea ice or bits of icebergs that have carved off the glacier. So I'm mainly focused on getting ice velocity on the grounded part of the ice sheet, but there may be people doing modelling or working to understand ice motion or other types of ice. And so this data that I would normally throw away could be useful to some people if that's what they're interested in looking at. And just wanted to point out this one because this is a massive iceberg that's just off Smith Glacier. It's been there for ages. But again, you can get a really pretty nice measurement of the motion of that iceberg if you wanted to from the Sentinel data, even though it would be something that I'd normally throw away. So the practical that you're going to do this afternoon is on 79 Fjorden. It's I think, really pretty ice stream in the northeast Greenland. This is a location map, and it's the green spot just up there. It's been in the news recently. Jeremy, who will be presenting later this week, and I think might go into this in more detail, had a really nice paper out in Science about the changes that have happened on this glacier. You've got Zachariastrom here, and I can't pronounce it. It's too long a word, but 79fjorden is the other way, the other thing that we can call it. But that one's flowing in this direction. You can see that there's two very distinct ice streams that are right next to each other. And the science story in this area, if you didn't read about it at the time when he had his paper out, is that the ice front has been retreating. So these green lines show that the ice front retreating over time. And they've also got some interferograms, and they've been able to measure a little bit of grounding line retreat over time. I think this is linked to ocean temperatures. So that's one of the reasons why this is a particularly interesting ice stream to look at. So I hope you will enjoy doing that in the practical. What you'll be doing is you'll be taking an image like this, you'll be extracting an area of the centre of that image, so with it, like within this bounding box here, and you'll be doing intensity feature tracking on it to get ice velocity results from Sentinel-1, so you'll generate that data set. And what you'll then be able to do is compare that to an estimate that I've generated from my Sentinel data sets, and you can see if you think it's right and see what the differences are. You'll also be getting the data from the CPOM Ice Velocity Data Portal to compare against, so you can compare your own data against something that we've generated earlier, Blue Peter style. And now I just want to hand over to Andrea so he can give you an overview of the toolbox that you'll be using to do this. So